Okay, well thank you for watching the last video. This video will be on 8.2, which discusses the surface area of solids of revolution. Okay, now recall that to make a solid of revolution, you'll take your function f of x, and then you take it from A to B, okay, and what do? You revolve that function about the x-axis and make a solid there. What we're going to do today is very similar to what you did when you actually found the volume. What we're going to do is we're going to chop the interval AB into a bunch of itty-bitty intervals. Okay, so we're going to use points x0 is equal to A, and then x1, x2, dot, 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 all the way to xn, where each xi minus the previous one is delta x, which is b minus a over n. Okay? Now, when we do that, we're going to get a bunch of little shapes. These shapes, if you can imagine, okay, each one of those little ones will be something like this, okay? And note that, much of the difficulty here is that this is not a straight line that we're obtaining there, okay? So what we need to do is we need to make delta x smaller so that eventually we make a figure that has so little width that this can't help but be a straight line there. Okay, and then we use approximating bands. Oh, I think my daughter likes math about as much as some of you, so we're going to look at bands that are like this, and we're going to find their surface area, and we're going to use those and glue them back together and get this figure. Okay? So what is the surface area of one of those bands? Well, each one of these bands has a low radius, so R1, and a high radius, R2, and a length, L. And that surface area formula is SA is equal to 2 pi RL, where R is the average of those two radii. Okay. So what do these things mean in relation to the graph that I just drew? Well, notice the radii is just the height of the function, right? So you're going to have, one of the radii is going to be f evaluated at the right endpoint. The other radii is going to be f evaluated at the left endpoint. Okay? And the L is going to be the length of the curve in that interval, which we just derived. Okay? So on the ith subinterval, SAI is equal to 2 pi f of xi plus f of xi plus 1 over 2, and then the arc length on the ith interval, which is equal to 2 pi f of xi plus f of xi plus 1 square root of 1 plus f prime at xi star squared d delta x, and then this has to be below 2 or above 2, and then making a note that if you have a function that's well enough behaved, if you take an interval small enough, that function is going to be essentially constant there. So what we can do is we can call this f of xi star plus f of xi star, which that'll make 2 of them, so that'll cancel the 2 in the denominator. So this becomes, or is approximately equal to 2 pi f of xi star times the square root of 1 plus f prime at xi star squared times delta x. And so the whole surface area is going to be approximately equal to the sum, I going from 0 to n minus 1, of the approximating surface areas, okay, which are, well, we've just written them down, 2 pi f of xi star times the square root of 1 plus f prime at xi star squared delta x. Okay, if we allow n to go to infinity, we have that SA, well, this becomes the integral there. Just like in the arc length formula, this is equal to the integral from a to b of 2 pi f of x times the square root of 1 plus f prime at x quantity squared dx. And that, folks, is your formula for the surface area of a solid of revolution. So let's go up to the top and write this down. Let f prime of x be continuous. The surface area of the solid formed by revolving y is equal to f of x, x from a to b about the x-axis is, SA is equal to the integral from a to b of 2 pi f of x and the square root of 1 plus f prime at x quantity squared dx. Okay, and we need f prime to be continuous. So let's do an example, and we won't belabor this too much, but we'll just ask you to set it up. So, example, because I feel like sometimes this is just another excuse to get you to do a lot of hard integrals. Okay, so set up the integral needed to obtain the surface area of the solid formed by revolving or rotating y is equal to sine of x, x going from 0 to pi over 2 about the x-axis. So the solution here, when they only ask you to set up the integral, don't try to evaluate it, right? Don't do too much work. So the surface area here is just the integral, x going from 0 to pi over 2, so you get 0 to pi over 2, 2 pi, f is sine, and going up here you have the square root of 1 plus the derivative of sine, which is cosine, squared of x, the dx. Okay, if one were to finish this off, you would let u be cosine of x, and then you would let, so like a u sub, and then you would let u be tangent theta, trig sub, and then you would use the fundamental theorem of calc and finish it off. Okay? But we don't ask you to do that here. So thank you for listening, and there will be 2 more Chapter 8 videos, and then we'll be done with Chapter 8 in pretty swift fashion.